The trouble is that when you square probability, it becomes smaller actually, not greater. So I can't say that the square of probability is bigger than or equal to probability. But I have some positive number in front of probability. So that positive number can also be between 0 and 1. Okay? So that would not be a kind of yes. I mean, if I know that if lambda is bigger than 1, here it's fine actually, because then lambda times p and its square would be bigger than lambda times probability. But I can't say it.
Product.
So that interval is anyway. Think over it. ठीक है जी. So what is the last inequality? So for last inequality, observe expectation of xt square must be less than or equal to expectation of x of t square. Would you agree with it? Because x square is a submartingale. Okay. You can also talk from this perspective that it's a submartingale. X square submartingale है. So this would be the correct.
Small t और capital T.
ठीक है. Small t and capital T.
Inequality 3 कर रहे हैं ना.
ठीक है. So this would be true. And if I take the supremum of expectation of xt square, where the t is between 0 to t, I know it's for sure less than or equal to also expectation of t square. But can you see that it would be exactly equal? Because with the t, this is a kind of increasing sequence factor, which is always bounded above by this number actually. So if you're going to take supremum, you have no other choice except saying that it should be equal to the x of t. Okay? And which also shows, and I know this guy is finite. So why we needed this square integral here? Because you should be able to then say that your z omega really makes sense of this supremum makes sense.
This means we're assuming this process to be L2 now.
Yes. I mean, if this is L2 and increasing, then yes.
वो तो more over.
But it's good in your. Okay. So why he is not assuming that the process is L2? So he is not assuming process is L2. He don't want to assume something that he can prove actually. It's really a philosophical point. Think about it. So why should I assume something that deduces from my assumptions actually? Okay, so I can deduce that this is L2 infinity. So why should I assume it? So this is the key point. An interesting point actually. You should always reflect on this. Then I can again use my previous discrete time theorem, and I can say that maximum of expectation of x square when j is in this indexing set xj square. So whatever we did with the x, now we are doing with the x square is less than or equal to 4 times of expectation of x square of t. So we have such an inequality for discrete time. Okay? Discrete time. So what would we like to do now? I would like to do this now. I would like to take the limits. Okay? So, but the maximum of j in d and p. Are we happy with this? So this is a discrete time inequality from previous cycle. Okay? But the maximum of j xj square d the path continuity converges to the supremum, okay, of 0 to t x square t. But this is nothing, expectation of x square of capital T actually. This is what.
Exactly.
Okay. So can I say it's with expectation? No, it's not
I
expectation.
don't know the frame. It is
Okay. Are we happy with this? So it's an increasing sequence, and the same argument is going to run again. So you can work this one. So if I so since you have the continuity of the paths, okay. So what happens? So in other words, I can take limit here, and this limit is going to be expectation of x square of the, okay, and I can expectation of x square of the expectation of z square of the, which is less than or equal to expectation of x square of the. ठीक है मेरे भाई? Are we happy with this? थोड़ा सा. Go from this step to this step. Path continuity is helping you. Okay, so you have continuity assumption. Okay, so just have a careful look on it. So now come to the point. So why we did all this messy kind of a proof actually? Because I would like to prove very interesting kind of a proposition about the Brownian motion. And this proposition is this. And you guys have to tell me. So it's a small proof, not a big one. I'm going to use one of inequalities out of these three. This is the inequality. So limit p goes to infinity. W of p is equal to 0. P almost sure. What are this proposition? Then W is a Brownian motion. So what are this proposition is telling? What's the interpretation of it? The interpretation of this could be that in long run, Brownian motion is going to, shall I say, weaker, roughly smaller than the values that WT is going to take in long run are going to be smaller than this linear expression. Because of that, this is becoming 0.
T dominant.
Okay. So T is dominant. Are you getting the point? So if this would be dominating, you're going to get something else. So T is dominating this value here. This is something very interesting that if you have Brownian motion in long run, it will be dominated, or it will almost behave like, not like, but it's gonna be worse than linear. Okay, you're not really always linear in that.
So how is this in physical nature? Like maybe we can take Brownian.
So here's the thing. So what does this mean? So you have this process and it's taking all these values actually. So it's T versus WT axis. Okay. So what does this is telling you that if you go long enough, this wiggly, so what will happen to the wiggly behavior actually? So it will get stabilized actually. And it will get roughly stabilized. This is what one implication of it is going to be, could be. So I'm thinking this. Okay, so if I draw, for example, okay. So this would be the line y equal to t. Okay. So what does this says? In long run, the value of the Brownian motion process is going to be
Lie
always
inside this.
below this. Okay. Correct me if I'm wrong. Okay.
You're very worrisome.
There are very good exercises which gives you a lot of very interesting piece of information based on this proposition about Brownian motion. So let's quickly prove it. Okay. Not going to take too much of time. Just quickly on to. Here's the proof. This is really important to go through this, pain of going through the formal proof. Actually, this is important. Otherwise, you can keep these facts in your head, and you will have no idea that what kind of things you're talking about. Okay. And once you do the proof, you start appreciating the authors. Actually, those who have done it for the first time. You know that they must have taken a lot of pain.
वतन की मैं सलाम करता
For doing that.
वतन की मैं सलाम करता हूँ
दुनिया की करती हैं।
So observe if you have instance S and T, in other words, U is an instant between S and T, then the expectation of, okay, maybe I remark one thing, just a quick review. So, here, this result is, so this 0 is not something special actually. So you can replace, so the result tells you, if you think carefully about it, that the important thing is not 0 and t, the important thing is the length of the interval actually. Okay? So if you take, for example, an interval instead of 0 to t, you take an interval s to t, the conclusion would still hold. Okay? So the conclusion would be true for any finite closed interval theorem. Okay? So there's a remark, you can also have a look at it, but you can see that why this shouldn't be true for any finite interval. So what's so interesting about, because have we used this zeros nest somewhere actually of the time? We haven't used it actually. You may start with something. Okay, so take an instant u that is between the interval 0 to t, then this previous inequality tells you that the supremum of u between s to t, okay, of u square of u by u, be very careful. My u looks like 4, so can be estimated by 1 over s square of expectation of supremum over the u in the interval s to t of w square u divided by s square. Would you agree with it? Why this must be true?
So it doesn't follow from any inequality, it's a general fact.
Kaise?
So u is greater than s. The square, very inequality with the square is on total w upon u, not only on w.
Okay.
So
U is your point. Yes.
Yes, sir. U is greater than s upon velocity.
So yes, you got it. You have a square. Okay, so this square is not on just this w, but this square is. So this is something that I now it's clear. ठीक है? Now this makes sense. Now this makes sense because u is less than or equal to s. On this guy now I can apply
This
the
inequality.
inequality, so this will be less than or equal to. I can say 4 times of expectation of W square of the t. Can you see t? So t is like the last constant of the interval.
That's true.
Okay, and divided by s square.
उसमें से जो है कि
You're taking reciprocal consumption.
स्केल ले रहे तो दोनों वैल्यूज कम हो रही
जी
है
जी.
दैट्स व्हाई देयर विल बी नो
But
प्रॉब्लम
still यानी वो inequality
यहाँ
preserved.
पे प्रिजर्व है
Inequality preserved. ठीक है भाई? भाई ऐसी बातें जो है ना किया करो यार. ऐसी बात You're taking it so thank you. ठीक है? The expectation of WT square, I know this guy is equal to what? So it's T actually. So 4T over ठीक है? So this inequality, so in other words, I can compute the expectation of supremum of this expression. You know, so this is a general estimate actually. So it could be any SNT. Okay? So now I would like to make a particular choice for SNT. So let's take S to be 2 raised to n and T to be 2 raised to n plus 1 actually. Okay? So let's take it. So what we will get from this inequality, so it's going to be the expectation of the supremum of the u between 2 power n to the 2 raised to n plus 1 of w of u over u का square. तभी कहते हैं late hours में क्लास नहीं होनी चाहिए.
Yes, sir.
Everyone gets, ठीक है? Equal to what would be 8 over 2 raised to n. This is going to be the estimate. And what does this show? As n grows, I can make it as much as smaller I want it. Okay, so I can make it as much as smaller I want as n grows. ठीक है भाई? Let's look.
हाँ सर
So take an epsilon positive. Take an epsilon positive. And observe this. Supremum of u in the interval 2 to the n and 2 to the n plus 1 over w of u over u square being bigger than epsilon square is true if and only if supremum of absolute of w of u over u being bigger than epsilon, where the u is in this interval 2 raised to n and 2 raised to n plus 1. Now we are happy with inequality, we are happy with inequality, and this is a generic factor. Hope you agree with it. That the supremum of this square bigger than the square would be true if and only if the supremum of this is true. See? And if this is the case, so for those omegas for which this holds, this must hold, and for those omegas this holds, this must hold. So if I want to convert into a probabilistic expression, I'm going to say that probability of this is equal to the probability of this actually. ठीक है? Probability of this. And I have an estimation. Can you see where I'm heading? So I have some kind of estimate on square of it, and you have equality with it, and from that I'm going to deduce what I want. Okay, so let's finish this proof. All right. apply that Markov type inequality that we had previously. So that if I use lambda to be epsilon, okay, and x with this process in my previous Markov type inequality, and I can say epsilon squared times the probability that supremum of u between 2 raised to n and 2 raised to n plus 1 of w of u over u square being bigger than epsilon square can be estimated. Okay. So it can be estimated by the expectation of the supremum of u in the interval 2 raised to n and 2 raised to n plus 1 times this w of u by u square. Are we happy with it? Okay. So this is like probability of, okay.
Pues mejorando.
Are we happy with this inequality? Okay. So if we are happy with this inequality, for this I have an estimate. What is estimate? This is less than or equal to 8 over, I can say 8 over 2 power n, but also divide epsilon square. Can we see what is happening? Anji? Anji?
So ये epsilon उधर का आया मगर ये
हाँ
किधर का? उधर का?
हाँ ठीक है
अच्छा ठीक है. Okay. So let's do this. But this is equal to by definition, not definition, but the observation that you made is this. So this means that the probability of supremum of w of u by u absolute, okay, being bigger than epsilon is less than or equal to 8 over epsilon squared 2 raised to n. Okay. So what does this mean? What should I do? How many of you people remember the Borel-Cantelli lemmas? याद है किसी को? याद आ जाएगा. Okay. Let me give this event a name an. Okay? So an is the collection of the omegas for which this is true. I'm giving this event an. And I know as n gets bigger, the probabilities